All right, it's also sort of the other direction. So we don't have Google Scale Compute. So this talk will be about what you can do with academic compute, but still be in this exciting domain of foundation models, multimodal learning, language models, vision language models. So this is the title of my talk. And actually, to make it proportional, it looks more like this, the academic compute being kind of tiny. And the motivation for this whole set of papers that I'm going to present today is instruction tuning. So instruction tuning is basically what makes the difference between GPT-3 and ChatGPT. So the raw LLMs, like let's say GPT-3 or GPT-2, they require, of course, substantial compute for pre-training, and the model by itself is pretty much useless. You cannot interact with it, you cannot do all that much. But once you add instruction tuning, which typically require just small instruction tuning data sets, you get these chat LLMs or instruction tuned LLMs that can do all sorts of things. And this process usually requires just a fraction of the compute. And this is what makes the large language models really useful, customizable, and better, and just generally wow, right? No one knew about GPT until ChatGPT came along. And the same goes for vision language models as well. Until we had GPT-4V and Lava models, like everyone was just using CLIP, and CLIP is fairly limited. So what can we do in the vision setting, right? And this talk won't be all about vision, but also include some LLM stuff. But generally speaking, in vision, already the models that we have pre-trained, let's say with Dino or with CLIP, they're quite useful. And still, they require a substantial amount of compute. But we can improve them further, also with something that requires a fraction of the compute, and make them better at all kinds of tasks. And this one I call post-pretraining. And this talk will be generally about post-pretraining. So, well, the questions we'll be answering are sort of what losses should I use? What kind of data shall we use for post-pretraining? And how can I be efficient in terms of the number of adapted parameters, right? And we'll be going through all of these questions today. The first work I'm going to present is called NeCo, Improving Dino V2 Spatial Representation in 19 GPU hours. So single GPU, 19 hours with patch neighbor consistency. And the title is pretty much the name of the game. So we take Dino V2, we develop a new loss, we further fine-tune Dino V2, and we get models that are better than Dino V2 at specifically dense understanding of images. All right, so it starts off with this question that we saw in the Dino V2 paper, where you can see that, oh wow, Dino V2 can sort of understand all these spatial similarities, right? If you look for where's the nearest patch of this horse drawing, it actually maps to the horse drawing. And this is amazing. But then if you actually play around with it, you often get results that look more like this. So if you try to find where's the nearest patch in terms of nearest neighbors from this patch, you would expect it to end up at like where at different kinds of ears, right? But instead, with Dino V2, you end up somehow getting this patch being the nearest neighbor or that patch being the nearest neighbor. And this green result is actually what we get out of our final model. And this is what you have with a state-of-the-art Dino V2 with registers model. So how can we get to this place at the top? This is where we come to the idea of patch nearest neighbor consistency, which is very intuitive to us humans, right? So let's say we have this red patch of the skater. So it's the right shoulder of this BMX rider. And now we have these 1, 2, 3 patches of different images. For us humans, it would be very easy to say roughly what the ordering should be, right? So right shoulder patches, they should be similar embedding, then maybe the left shoulder patches, and then everything else. That's very easy. And now the question is, can we make this somehow a loss? And the answer is, yes, we can. That's what we do with our paper, Patch Nearest Neighbor Consistency. It's basically this idea that I just told you, but put into a self-supervised learning framework. So we start off with a pre-trained model, in this case Dino, and we further fine-tune it. And we fine-tune it. We have, again, this teacher-student setup with an exponential moving average. We encode the images through the vision transformer, and then we get the dense features out. So in the case of 224 by 224 images, and you turn them into patches of 16 by 16, you get finally like 14 by 14 dense visual features out. We do the same for images from the badge, so we get what we call reference patches. So these will be just used for comparison purposes. You can think of them kind of like negatives in the SimClear framework. They serve a similar role. And now, because the two views had different crops, so for example, here you can only see the croissant, here you can see the croissant slightly in the left-hand corner, we do an ROI align, such that every croissant pixel is aligned to every other croissant pixel. Now, next what we do is we compare the distances of the features that we had in the reference compared to the patches that we have inside the image. And this is simply where we do the dot product and we subtract 1 minus the dot product. And then we do differentiable sorting, which basically now says, okay, if you had to sort the similarities from this image patch that we have, so from the croissant, for example, and then you try to compare it against all the patches from the batch, how would you sort this? And now the crux is we say these two should be the same no matter whether you start from the top view or from the bottom view. And so this is the loss. So for every patch, we compare against every other patch in the references and say these two sortings should be the same. So it's a very dense loss. So in terms of number of patches, if that was P, and we had number of references, could be R, it's P times R loss terms. And references are, let's say, batch size 64, and each image has 196 patches, so it's like 12K loss terms from a single batch. So it's a crazy dense loss in a way. And that's what exactly helps us train in 19 GPU hours, because it's very fast. You get a lot of signal out of just a few images. So in terms of evaluation, we do a bunch of things. This is one of our main evaluations, which is called visual and context segmentation. It's been proposed first in the Hummingbird paper from DeepMind, which was at NeurIPS 23. What you do here is you embed images through a frozen backbone. Then you get all of these dense features. Again, just as I said. And now for any given query patch, let's say you now want to segment this image. For every patch, you also put the image through the backbone, and now you try to find the nearest neighbor within your training data set. So again, you find, for example, similar neighbors. If it works well, these would be your similar neighbors in your training data set. And now you simply look up what are the annotations for these training images. So in this case, for example, the training annotations for this patch might be shoulder, and here hopefully is also shoulder or human. And then you simply do nearest neighbor retrieval and get the annotation this way. And this way you can do semantic segmentation with frozen models, which is a very nice way and sort of resembles in context learning for large language models. All right, if we do this, we can see that we get pretty strong gains. So we start off with a Dino V2 with registers backbone. So that's our starting point. So indeed, we hopefully improve upon it, and we improve upon it by quite a large margin, even if you use a fraction of the data sets. So if you just use 1 over 128 of the data set, we still are better than, let's say, if you use 1/8 of Pascal VOC for semantic segmentation here. Yeah. And the same goes for ADE 20K. That was first evaluation. You can also keep the backbone frozen and just train a linear decoder. That's another common way to evaluate how good is the representation. And also in this case, we get pretty large gains compared to the original Dino V2 with registers, which already was like 10 percentage points above the previous state of the art. So this gives really good gains on these dense tasks. Same, you can do this also for fully unsupervised semantic segmentation. You also get large gains. All right, but Panico or the NeCo method is not reliant on having Dino V2 with registers. You can apply it to all sorts of previously trained backbones. So you can apply it to iBot, you get gains. So everywhere where you see blue numbers, it means we get gains, which is everywhere. So you can apply it to Dino, to time tuning, to Leopard, and also to Crybo, which is also a method which has been trained in a dense fashion. It boosts the performance of all these methods, even under like fairly limited evaluation protocols like clustering evaluation or linear probing, dense linear probing. Qualitative results, we'll skip this one, but you can see, well, yeah, you can see that Dino V2 with registers, if we take a random patch from a horse, it retrieves all sorts of random images. So here, indeed, there's a horse, but it doesn't really match. Here, in the case of ours, it matches all the things you retrieve are basically horse patches, and they also match in terms of location pretty well. Same for this horse rider. You have the patch of a face, but Dino V2 with registers retrieves all sorts of other patches. And here we didn't limit it to only retrieving different patches. So it basically just says these two images are so much the same that all the nearest neighbors come from this single image, which is kind of strange. Same for this one. So from this paper, essentially what we propose is this dense patch ordering as a self-supervised loss term, which converges pretty quickly and can improve upon the very strong Dino models, especially in the in-context semantic segmentation tasks, but even for full fine-tuning. And of course, code and models are available. All right, so the next work is PIN that was accepted at CVPR 2024. And by the way, I'm sort of incorporating a bunch of pictures from Nuremberg here because that's where our lab is located. Yeah, this work is about vision language models and how to fine-tune them to do new things they couldn't do before without any supervision. So if you take naive vision language models that were only trained with captions, so not the ones where you put in bounding box or localization data set, but just the ones which have been trained on the web, like the early ones, Flamingo, or the first stage of the Lava models. And then you ask them, provide a bounding box around the cat, or you ask them, localize the cat in the image. These are the sort of results you can get. So with GPT-4V, you would get sort of a bounding box out of it, but with the second prompt, it would already answer something like the cat in the image is sitting on the right side and keep talking, even though it's kind of wrong from the image at least. From the perspective of the plant, it might be correct. Or if you ask Open Flamingo, it will just answer some random stuff like the cat in the image is localized in the image. Yes, okay, very helpful. So this is not really what we want from our VLMs, right? And Fromage is even worse. It just answers, yes, you can do that. Or Blip2 doesn't even answer. So all of these early vision language models, they don't know this data. They cannot solve this task at all. But we argue that actually this ability is somewhat in the pre-training data already. So we just need to unlock these abilities in VLMs. And this is what we are trying to investigate. So can we somehow unlock the forgotten localization abilities? And this is sort of the hypothesis. Can we somehow make these VLMs, which apparently cannot solve the task? And so what we do is we take the frozen VLMs, such as Flamingo or Blip, and then we insert a new learnable module, which is a parameter-efficient fine-tuning method specially designed for vision language models, called PIN module, which I'll get to in a bit, and some synthetic data, which does not have any human supervision or annotations at all, to make object localization work. So the pipeline is as follows. We first generate this sort of data, where you simply paste objects that were created using stable diffusion onto random backgrounds. So because we paste this stuff on random backgrounds, we know exactly where an object is, right? So we kind of get a synthetic, fake bounding box signal out of this. And of course, you can see that it looks pretty fake, right? It doesn't look natural at all. But since we keep most of the backbone and we keep the complete vision backbone frozen, it really doesn't matter. It cannot overfit to these pasting artifacts. So that's the data we use. It roughly looks like this. It's pretty crazy, right? It's all kinds of categories painted together. And one thing also that was important to us here, we generate the training data with a fixed set of categories, and we evaluate on a completely different set of categories. So all the evals we do is actually zero shot in terms of the categories that have the model has seen. So this is, I don't know how many of you know this. This is a default pipeline of the Flamingo model. So you have an image which gets encoded via a vision encoder, and then you have a fusion network, which is essentially cross-attention to multiple layers of the LLM. And the LLM works by, of course, first tokenizing the text and then being able to output text. We, instead of giving raw images, we give these sort of fake synthetic images out. And now our model, our PIN, the positional insert module, simply modifies the visual features. So the visual features are this latent box, right? So in the case of 224 by 224 images, these are 14 by 14 by 700 dimensional features for like a vision transformer. And we simply add another box of features to this. So this is element-wise addition that we do here. And I'll tell you in a second how this is done. But then you get these modified features out, and everything else is frozen, right? Everything that's gray stays frozen, and we're not touching it. So we're not touching the LLM. We're not touching the cross-attention, not the tokenizer, not the vision model. We're only adding like something linear to the vision encoder's features. And then we're training it to do next token prediction for the actual bounding box location. So this is the same way how you would train in the LLM setting. You're just predicting the next word. And in this case, the next words are these literal strings of 50, 120, and this is how we train the large language model. So there's no linear layer which outputs regression targets or anything like that. It's all in the VLM setting. And now the positional insert module itself, how do we get to this box? We simply take a sinusoidal embedding, wrap it around in a square, such that it kind of tells the model which position is, and then it's simply a convolutional MLP. So we simply slide this MLP across all the positions, and then you get this feature box out of it, which is a very efficient way. So I think overall it takes less than 1 million parameters or 60,000 parameters for this pin module for adapting these like billion-sized flamingo models. And yeah, these are some of the results. So here first on some non-realistic, photorealistic images. So it can pretty well localize person, boat, apple, pineapple, all of these sort of things. Even though we didn't train on these categories at all, this sort of knowledge is still encoded in the vision language model from the first stage of where it was trained with captions. And funnily enough, it can also do things like Tom and Jerry, right? So this can only happen because the model knows from the language pre-training what Tom and what Jerry is, which is pretty neat. We can also evaluate this on some existing data sets like Pascal VOC, QUVA, and so on, and actually beat other parameter-efficient fine-tuning methods such as LoRa or visual prompt tuning on these data sets, even though we're very limitedly intervening on these latent representations that are between the vision model and the language model. And we can also evaluate on RefCoco, which is like one of these data sets where you can actually evaluate referential localization, which typically looks like something like, give me the location of the left black shirt. And then what you need to predict is this blue bounding box, and our model actually predicts the red one. And so this one, for getting an evaluation on this data set, we slightly modified by including left and right in our training data. So if we sometimes paste, for example, 2 monkeys into an image and then say the left monkey, and it needs to predict the bounding box of the left monkey. So all of this is basically fake data, no supervision, no human annotations at all, but it can sort of, it's starting to solve these tasks, even though it didn't have access to all of the data. All right, we'll get to questions in the end. I think that might be a better way. I'm gonna just keep going. Next talk is called VERA, Vector-Based Random Matrix Adaptation. This has been presented at ICLEAR 2024, and it's a parameter-efficient fine-tuning methods for transformers. So it applies to vision transformers, it applies to vision language models, it applies to LLMs. What are adaptation methods, perhaps? Maybe let's start there. So all of these big tech companies spend billions of dollars, lots of GPU hours, use lots of proprietary data to make these large models, right? And adaptation methods allow us to do something with these big models. So these are basically our lever in order to move these, in order to train these, in order to customize these models to all sorts of new settings. And just as a comparison, so if these large models are in the 7, 13, or 32 billion range, these models are in the million or even less than that range. And it's pretty crazy that we can steer the behavior of these models so well if we place some learnable parameters in just the right locations. And this is one of those adaptation methods papers. I also saw yesterday there was another one. I only saw the slides, but I wasn't quite here, but LoRa XS is also one of those. Right, so we all start with this motivating paper LoRa, which I'm sure plenty of you people know, but it's essentially you keep the initial transformers are all about matrix multiplies. Matrix is W. Instead of adapting the matrix W, which has a lot of parameters, we're going to adapt 2 learnable parameters, A and B. And the crux is that A and B share this one low dimension, which is R. So instead of learning D by D, you learn 2DR number of parameters, which can be a lot less if R is smaller than D. This is LoRa. Very nice. You learn A and B per layer. The only thing is it's low rank, but it turns out for pre-trained models, low rank adaptations are fully enough. All right, what we do in Vera is very similar, as you can see, but we're keeping a lot more frozen. So actually, we're keeping this A matrix and B matrix completely frozen and randomly initialized, and they're actually shared across layers. What this means is that you never need to store A and B, actually. All you need to store is this random seed, which is a single number, and then you can recreate the A and B matrix. And what we learn instead are these two vectors, D and B. And these two vectors scale the matrices, right? So they can be seen as random scalings of the rows and column vectors of the A and B matrix. And this turns out to be working really well. There's this whole literature of random matrices and random Fourier features which work well. So there's some theorems and lemmata as well that random projections actually preserve the structure of data quite well. Not going to go too much into detail there, but if you wanted to, you could actually motivate randomly initialized matrices quite well. There's a bunch of these LoRa methods which recently came out which also use random matrices. They're here in bold, including like our method here and the more recent ones. I only added the recent 3 here, like Dora, PISA, and LoRa XS. But there's plenty. Like there's plenty more even that have came out. But yeah, plenty of them use random matrices because they're super cheap, they're super expressive, and quite interesting properties. And yeah, we get quite good results compared to all the previous methods, even with like tiny amount of parameters. So in this case, it's like 10x less than LoRa. In this case, it's less than half of LoRa, and we still outperform them, even for things like instruction tuning, which was just starting when we put out the paper. We managed to do 100x less parameters to still get better or same performance depending on the model size of Llama 2 back then. So yeah, this and it also works for vision transformers as well. Here is a plot for that. So here we're starting with a MAE backbone and simply doing either fine-tuning of the head or full fine-tuning or Vera-based fine-tuning or LoRa-based fine-tuning. You can see it doesn't really matter which method you use. They all perform basically the same, except that ours like requires a lot less parameters. And of course, these sort of adaptation methods are getting much more popular. Even Apple recently, I think a couple of months ago, had this blog post that they use adapters on the phone. They have multiple adapters on device because they're super cheap to store. And I think with these sort of extremely cheap adapters, we will get to a space where we have like hundreds or thousands of adapters on your phone, which all do very customized things, all leveraging this one pre-trained backbone that can be used for all kinds of tasks. Right, and of course, recently the Dora method came out, which is essentially applies the weight norm trick to the LoRa matrices. So it learns the direction of the LoRa matrix separately from the magnitude of the LoRa matrices. And actually, as they show, it's also combinable with Vera. So some of these PEFT methods you can also combine nicely together to achieve very low parameter counts, but still strong performances. And we have the code available. It's also included in the Hugging Face PEFT library, which we're very happy about. So it should be very easy for you to just implement it in 3 lines, essentially. All right. Let's see. All right. I'm already, last paper, but hopefully you'll have plenty of questions. All right. This paper will present at NeurIPS 2024, and it's the first time I'm presenting this work. So let's see. So the paper is called No Train All Gain, Self-Supervised Gradients Improve Deep Frozen Representation, and it's a collaboration with Valio AI. And the main author is Walter Simoncini. Right, so of course we all know that the loss of a neural network usually indicates how the network output should change to solve a task, right? And that means the gradients we get from this loss carry the information about the current network status, the task, so what are we trying to solve, and the data, because that's where we generate the loss from. So from this just very boring description that you all have heard in some basic deep learning course or blog post or tutorial, actually there's this one idea, like why not use gradients as features, right? They contain so much information. They contain all of the information about this. So why don't we just have the gradient, which is for every parameter in the network, turn this into one vector and use this as a feature? And this is sort of the basic idea of the paper. And the spoiler is that actually those features are very good. You can use them for all kinds of things, and they're complementary to the features you get from simply having the embedding come out of a neural network. However, traditionally, you would need a loss that requires supervision, right? Like in this case, you would need labels for an image. That means you need to have a labeled data set, which is, especially if you're trying to do k-nearest neighbor of some new data point that you don't have, you obviously don't have labels, right? So you cannot really get a loss out. So it wouldn't make sense. However, this is where self-supervised learning can come to the rescue. You actually don't need a label for this. So you can simply apply a self-supervised learning loss on any data point you have, even though you have no idea what it is. And you can even play around because there's all kinds of self-supervised losses nowadays. And it turns out they're nicely combinable. So if you apply a contrastive-based gradient, or a contrastive-based gradient has information that's not contained in a dino-like gradient, for example. And we'll later combine these to get even better representations. So how does it work? So here, again, we have our image. We turn it into patches because we work with VITs. And then we have our frozen transformer. And then we have some sort of head. This can be a linear head, for example, randomly initialized. And what I'm showing here is how you get the gradients for like a SimClear-like method, right? So in the case of SimClear, you get this feature out for the image, and then you're trying to repel against negative batches. And actually what we do here is we apply multiple augmentations, so we get multiple views for every image, and then we compare it against all the negatives, which we simply have from a fixed batch from the data set. We know it's not the same images, right? And then you get these gradients. And we extract these per sample, and then we're gonna forward an image, compute self-supervised loss, and backpropagate, and then extract the gradients with regards to the weights of a layer. And we typically use one of the last layers because that's where most of the semantic information is contained. And then we downsample then. And then we're going to project the gradients and obtain this fungi. So feature from unsupervised gradients. This is a fungi. And this is all because the gradients themselves, they're pretty huge. So for a matrix multiplier 700 by 700, this would be a lot of a huge vector. So instead we just apply a random matrix. Again, random matrix is very useful to project it down to something manageable, like 700-dimensional vector. And now what we do is we combine three objectives. So if we had this vector that points to the embedding, we now get the vector, we now get the gradient from SimClear, Dino, and Kalbeck-Leibler divergence. And we can simply concatenate all of these features together, get like a, let's say, 4 times bigger vector, and then reduce the dimensionality again with PCA. And then we simply put it into our database, right? So if we want to do k-nearest neighbor, we always just build a database, and that's where we do the retrieval from. The final feature we get is not bigger than the original embedding, so it's still 768, but now it mixes gradient information as well as image embedding information. And as we'll see later, this is pretty powerful and robust and can counteract some of the negative stuff. In practice, it looks like this. So it's really simple. So we made it available as a library. So you can basically call fungi wrapper, initialize your model, set which target layer you want to extract the gradients from, set the device, and then say what kind of gradients you want to have, let's say Dino or the KL loss, and then you get the fungi features. So it's as simple as this. And hopefully plenty of people will start using it because of the advantages that I'll show in a second. But before that, let's first investigate some of the properties. So here we check out what the accuracy on a couple of data sets, so flowers, satellite images, and cars for k-nearest neighbor retrieval, and look at what happens if we combine embedding with KL, or embedding alone in this case, or if we combine embedding with SimClear and so on. And we find out that basically every time we combine the embeddings with some gradients, we get better performances. So the gradients carry some information which is complementary to the embedding alone. The gradients have some information that's complementary to the embeddings alone. And actually, they encode quite different things. So, for example, in this case of SimClear plus, so SimClear plus KL, it works actually the best compared to SimClear alone or SimClear plus embedding. So there's quite some useful information contained even in the embeddings alone. So even if you don't store the, in the gradients alone, even if you don't store the embedding, you can actually get really good features out of the gradients. All right, and we have quite an extensive experimental suite, 20 backbones, 22 data sets, and across vision, language, and audio for a total set of 1,000 experiments. So yeah, let's take a look at some of the results. So here we do k-nearest neighbor classification, and here the accuracy is shown as an average over 11 data sets. So it's pretty robust, these results. And we can see that we get large improvements for K and N, even for very strong models like Dino V1, Dino V2, or CLIP backbones. For the few-shot setting, where we take 5 images per class, we also get very strong improvements, up to 5% better for CLIP and for 5% better for Dino V2, essentially. Even for language, in the case of classification here, we get strong improvements, basically almost everywhere, and even for this particular data set, even 12% better performances. Or same for the few-shot case. For the audio, we start off with an audio pre-trained self-supervised backbone and do the same trick, again, Dino and contrastive loss, and we get gains for audio classification. And we can do the same evaluation that we did earlier, where we try to retrieve the nearest neighbors, right, in the visual, dense visual space. This is called the hummingbird evaluation. And even here, we get large improvements. So here you can see what happens if you do this with Dino with only the embeddings. So these are the numbers that people have previously used, right? And now we simply take Dino V2 and apply our fungi features to it. And you can see we get very large improvements on all of these benchmarks. Importantly, we can compare this to the state-of-the-art method, which was trained exactly to perform well on this task. And we can see that despite ours not requiring any training, so we don't adapt a single parameter, right? We actually get almost the same as the state-of-the-art if we have a large memory bank. So the performance delta is very small at this point. And all of this is without having adapted a single parameter, right? I mean, computing the gradients is still expensive, and then storing them, okay, fine. But still, we haven't adapted a single parameter. So that's one funky thing about this paper. Yeah, and this in-context semantic segmentation that I've been talking about, this hummingbird evaluation, you can, of course, nicely take a look at the results. So in this would be, if you simply do this for Dino, looks pretty strong. If you apply it to fungi, you just see it's looking a bit better. It's still not as perfect as the ground truth, obviously, but you can see it starts filling in those holes pretty nicely, despite having not adapted any parameter. It even works for RAG sort of settings, so retrieval augmented generation. So in this case, we're doing this on the banking 77 dataset and giving GPT-4o mini some examples that we get from fungi compared to just from the embeddings alone. And we can see that actually we get a 2.5% improvement, basically at this point, the banking dataset being almost solved in this case. And we have some other evaluations as well, like even linear probing improves upon this. So for those familiar with like evaluating vision backbones, linear probing is sort of the metric that people use because it's pretty robust. You can see that basically everywhere the orange bar, actually everywhere the orange bar is higher than the blue bar, which means having unsupervised features, unsupervised gradients as features improves the features even under the linear probing protocol. So what does it mean? Self-supervised gradients are pretty useful as features, and they definitely perform better than just using the embedding alone, even though we're not applying more storage for the feature KNN database. Everything else is basically the same. And combining gradients and embeddings produces very strong features for retrieval, classification, clustering, and semantic segmentation, and it works across modalities. And the code is available. We'll present this at NeurIPS. And yeah, so sort of the summary is all of this was done in very academic settings, right? I think this post-pretraining has huge potential. So this is sort of where I started. Let's do something like instruction tuning, but in fact, it's a lot more, right? It's how can we adapt the models in a smart way using dense losses that people didn't do at scale. How can we do new tasks that the model couldn't do, but without applying supervised data sets to this. So that was the VLM paper. Or how can we adapt models in a very smart way with requiring very few parameters? It was a Vera paper. And lastly, yeah, can we do something from frozen models and make them better without even changing a single parameter? Yeah, so that's my talk. Thanks for listening. I'm happy to take questions now.